Okay, we're continuing our discussion on sound and sound waves, and we're going to start looking at the way sound waves can be affected, specifically looking at musical instruments is a good it's a good way to look at sound waves because they produce clearly distinct tones or pitches, and it's something that most of us are familiar with. So a guitar is a great way to start because a guitar makes a sound by vibrating a string, and that vibrating string can be used to um, imagine the wave itself. So if I were to try to sketch on here, let's see. There we go. So when this string vibrates, it creates a standing wave. It begins and goes down, and if we were kind of to continue that wave, it would come back up, and so we would have this this full wavelength here. And so if we just pluck the string, the way it vibrates, the length of the string is equal to half of the wavelength. And then the way a guitar works is you hold the string down on the fretboard and you essentially shorten the wavelength. So now the wavelength isn't as long, and it creates a higher pitch. The other way to create different pitches on a guitar is by plucking strings of different density or different thicknesses. So there are 6 strings on a guitar. The low E string is the thickest, and the high E string being the highest, the thinnest string. So those are 2 ways that you can affect the pitch of a note played on a guitar, by shortening the wavelength and by using a string of various thicknesses. So a piano is somewhat similar to a guitar in the fact that its notes are made by not plucking but hammering these different strings on the inside here. And again, just like a guitar, the strings are of different length. We can see down here, this string is longer than one of these short little strings over here. Excuse me. But in addition to the length of the string being changed, they're also of different thicknesses, just like a guitar. So we have heavier, thicker piano wires on the low end, and thinner material, thinner wires at the high end. So let's look at an example problem where we considered the possibility of a piano whose strings are all the same thickness. If we only depended on the length of the string to affect the pitch and not the thickness, what would that look like? So the problem statement here says that the highest note has a frequency 150 times higher than the frequency of the lowest string. And if the highest note is only 5 centimeters long, how long would the longest string need to be, assuming that it's under the same tension? I guess that's actually a third way to affect a note. If we go back to the guitar example here, a guitar has these tuning pegs on it, and they can be adjusted to tighten or loosen the strings, and that tension affects the pitch of the sound wave. So we're going to assume that everything is under the same tension. All the strings or wires are the same thickness. The only way we can affect the pitch is by changing its length. So if we want a note that is 150 times higher than the lowest string, how do we do that? So we're going to introduce this formula. It's based on a lot of the concepts from the previous chapter of velocity and frequency and the density of the material through which the wave is traveling. and we can use this for stringed instruments, that the velocity of the wavelength or of the wave is equal to the square root of f sub t over mu. So in this formula, the f sub t is the tension on the string, and mu is the mass divided by length of the string, which roughly corresponds to the density of the medium. So a heavier string is going to have a higher mu than a thinner string. And so in this particular problem, we were told in the problem statement that the tension of all of the strings was the same. I'll just write same. And the thickness of all the piano wires is the same. So if the tension is the same for all the piano wires and the thickness of the piano wires are all the same, then that means they all have the same velocity. So we can then go back to our chapter 11 formulas for waves and look at frequency equals velocity over wavelength. And so the frequency is going to be 150 times greater for the high string than the low one. And the length of the string itself is related to the wavelength. Remember, in this case, when we have a string that is vibrating at its harmonic frequency, it creates a standing wave where the total wavelength here is double the actual length of the string. This vibrating string is half of the wavelength. So, so the wavelength is equal to twice the length of the string, and the string is equal to half of the wavelength. So I could rewrite this formula as frequency equals velocity over 2L. And since the velocity for each of them are the same, both the high note and the low note have the same velocity, what I can do is I can rewrite this formula. I can take this over to the other side. So I've got 2L, so I'll use a script L, 2LF equals the velocity. Okay, but since the velocity of both the high and the low notes are the same, they're both equal to the same velocity. So I can write 2L, I'll use the subscript H to denote the high notes, and that's going to be also equal to 2 times L low, the low length of the string, and the low frequency. So these two things here are equal. It's just kind of like if A equals B and B equals C, then A equals C. So essentially, I've just said that 2LH, FH, so the low frequency, the high length of the string and the high frequency equals 2 low length of the string times the low frequency. I can just delete both or divide both of this equation by 2 to get rid of that 2. So I've got this relationship of LHFH equals LLFL. And so if I divide both sides by the low L sub L, and I divide both sides by F sub H, both sides by F sub H. These will cancel out. These will cancel out. And I'm left with a ratio of the high length of the string over the low length of the string is equal to the ratio of the low frequency to high frequency. And kind of doing this unscripted, and it kind of shows because I accidentally ended up here with my ratio of frequencies inverted from what I really want. I'd like to be able to say that the high frequency over the low frequency is equal to 150 rather than L over H is 1 over 150. So all I really need to do is flip these two ratios. That will remain true if I flip them around. So what I really wanted to show here is L sub L over L sub H is equal to F sub H over F sub L. So why did I do that? Because I was told in the problem statement that the ratio of frequencies, the high frequency compared to the low frequency, is 150. FH is 150 times higher than the low frequency. So I've got 150 equals the ratio of the low string over the high string. So I've kind of run out of room on this slide, so I'm going to go to the next one and continue that thought here of 150 equals L sub L over L sub H. And if I just take this over to the other side, then L sub H times 150 is equal to L sub L. So I've basically done all this mathematical manipulation. I've jumped through all these algebraic hoops, basically just to arrive at this conclusion that the low string is going to need to be 150 times longer than the high string. And we were told in the problem statement that the high string was, what were we told here? Jump back, 5 centimeters. Okay, so 5 centimeters is the length of the highest note. We've got 5.0 centimeters, which would be equal to 0.05 meters. So the length of the lowest string on the piano would have to be 150 times longer than 0.05 meters. And 150 times 0.05 gives us 7.5 meters. So if a piano did not use wires of different thicknesses, and if they were all tensioned exactly the same, then the piano would need to be at least as long as wire, 7.5 meters long. That's like 25 feet approximately. That is a giant piano. So obviously that proves why pianos are not made this way. We do use strings of different thicknesses and different tensions because otherwise the piano would need to be 25 feet long. That's a piano. So we're going to kind of continue with this idea of notes and pitches using musical instruments. We're going to transition over to air, air going through a column, like through a wind instrument, like a clarinet or flute, as pictured here. But I think we're going to have to start that conversation in the next video.